If a chemical equation is modified, the equilibrium constant will change. And what we're going to do in this video is we're going to take a look at 3 common modifications and the impact they have on the equilibrium constant and the equilibrium constant expression. So let's take a look at the first scenario. We are going to reverse the equation. So if we have the chemical reaction, the generic chemical reaction, A plus 2B gives us C, with the equilibrium constant expression equal to the concentration of C over the concentration of A times the concentration of B squared. If we reverse the equation, then I'm going to rewrite this. So we have C gives us A plus 2B. Now I'm going to rewrite the equilibrium constant expression with that reversed equation, and you can see what happens. We have the concentration of A times the concentration of B squared over the concentration of C. So you can see that the numerator and the denominator just switch spots. If we reverse the equation, the numerator and the denominator switch spots. Let's put some numerical values here. So say our first equation, our first reaction had an equilibrium constant of 50. That means that if we reverse that, our new equilibrium constant will be 1 over 50. So writing an overall rule for if we reverse the equation, the equilibrium constant will be the reciprocal. The new equilibrium constant will be the reciprocal of the old one. So our new one will be 1 over K. Now what happens if we change the magnitude of the coefficients? So let's take a look at the same exact reaction. We have A plus 2B gives us C, with that equilibrium constant expression of the concentration of C over the concentration of A times the concentration of B squared. Let's just say for this scenario, the equilibrium constant is equal to 10. Now, if we double the coefficients, let's take a look at a new reaction, but with the coefficients doubled. We have 2A plus 4B gives us 2C. Now I'm going to write that equilibrium constant expression with the new coefficients. And actually, those coefficients now become superscripts. So we have C raised to the second power. And that's all over A raised to the second power times B raised to the fourth power. Everything got raised to the second power, or to more of a power of 2. So that means our equilibrium constant needs to be raised to the second power, which would take 10 squared and make that equal to 100. So if we were to overall write a general rule for doubling the coefficients, if we double the coefficients, that means we need to take the equilibrium constant to the second power. We can take that rule one step further. What if we triple the coefficients, or quadruple the coefficients, or take the coefficients times any value? We'll call it n. So the coefficients of our chemical reaction times n. What that does to the equilibrium constant is it raises it to the power of n. It raises it to the power of that n value. So that's our second modification. Now the third one kind of ties in Hess's law a little bit. We're going to add reactions together. So what happens if we add reactions together? What happens to the equilibrium constant when we add 2 reactions together? So we have A gives us 2B, that's reaction 1, and 2B gives us 3C, that's reaction 2. I'm going to stack these 2 reactions on top of each other because that's how I'm used to showing how to add reactions together, so we can easily see what's on the product side and the reactant side, and we can cancel out what the same terms on both sides. So we see we have a 2B is a reactant and a product, so I can cancel out the 2 B's, giving me A yields 3C. I'm going to rewrite this reaction. This is the sum of the 2 previous reactions. A yields 3C. And I'm going to write the new equilibrium constant expression for that reaction. So K is equal to C raised to the third power over A, the concentration of A. Now we can get this new K value, this new equilibrium constant expression, without even finding the sum of the reactions. And the way we do that is, I'm actually going to erase what I have here and make the first equation K1 and the second equation K2. And I'm going to multiply these two equilibrium constant expressions together, and you'll see what the product is. So we have B squared over the concentration of A, and that's K1 times K2, which is C to the third power over B to the second power, the concentration of B to the second power. If we multiply these two together, the B squared values cancel out, leaving me with the concentration of C to the cubed power over the concentration of A. So what happens if we add two reactions together? What happens to their equilibrium constants? Well, those equilibrium constants get multiplied. So if we add two reactions together, the equilibrium constants all get multiplied. So I have K1 times K2 times whatever number of equilibrium constants I have for each individual reaction.